Hello and welcome to this video on waves. Specifically, we're going to be talking about sound. We're going to prove that sound is a wave first, and then how does it propagate? How do we make sound waves? And how is it different than the waves we've been dealing with? To start, how do we know sound's a wave? Well, we've talked about a couple properties of waves, things that are almost exclusively tied to waves. Frequency, interference, diffraction, refraction, and the Doppler effect. So if sound has properties of waves, therefore it's a wave. It seems slightly circular, but it's how we go about proving it. So frequency. How does sound demonstrate this property? How do we know sound has a frequency? Well, if you listen to different notes, you can hear the difference. The pitch of a noise, the pitch you hear is the frequency of the wave. Interference. This one's really easy. There's two ways you can go about it. First, we can talk about noise canceling headphones. When you have noise canceling headphones, they take the noise that you have coming in and emit a tone that directly interferes, destructively interferes with the incoming noise to make the incoming noise lesser. It makes it easier to hear because it cancels out the noise. If you want to go a little less high tech, think about when multiple people start talking. It gets really hard to understand, distinguish between the sound. That is interference at play. Because there's so much different sound and so many different cadences and pitches, the overlap is very hard. That is because they're interfering with each other. Diffraction, the tendency for a wave to spread out as it goes through a slit. Let's talk about hallways. When you're walking through a hallway, you can hear people talking from around the corner. Sure, it's quiet, but you can hear it. That's because the sound wave is approaching the corner of the hallway and then diffracting around it and spreading around so it can be heard. The fact that sound can travel through an opening, even as wide as a hallway, and still be heard around the edges is an excellent piece of evidence that it's a wave. Reflection is an example that you're all familiar with. Echoes. Sound wave goes out, bounces off a wall somewhere, and comes back to you as an echo. Now, because it's traveled great distances, because it's gone so far, it's quieter, but it's still there. Refraction is a little harder. If you've ever swam before, been sitting underwater while someone's trying to talk to you in the air or above the water, the noise sounds distorted, muddled, because as it moves from the air into the water,
it refracts.
Swimming is your example here. And then finally, the Doppler effect. Have you ever been in a car and heard a siren behind you? Maybe it's someone coming to pull you over, or more likely it's a fire truck or ambulance heading past you to a scene. And you notice as the truck's approaching you, the siren gets louder, more annoying, higher in pitch. And then it passes you and it gets quiet again. It gets far less annoying and far less intense. That's the Doppler effect in action. In fact, the sirens are pointedly designed so that way the pitch of the siren gets higher and more notable as it gets closer to you so that it's harder to ignore. Every property of wave we've looked at and investigated to date, sound demonstrates. So we have fairly good evidence at this point that sound is a wave. Using the logic of it looks like a duck, walks like a duck, talks like a duck, it's probably a duck. If it looks like a wave, sounds like a wave, and moves like a wave, it's probably a wave. So how are sound waves made? Going back to talking about guitars for a second and standing waves, we've talked about how if you vibrate something in the first harmonic, it will vibrate at a particular frequency. Guitar strings are the example we used. As the string vibrates and bounces back and forth, it's not just vibrating into nothing, it's hitting the air molecules. And as those air molecules get hit, they bounce off the string and then bounce off and hit the next air molecule. Upon the collision, the first molecule will bounce back and the second one will continue on. And this pattern of repeated collisions spreading out will eventually make a sound wave. Let's take a look at what this looks like on a larger scale. So here we have a simulation, a PhET simulation again, and we have air molecules moving through the air, and they're generally just standing there, shaking, doing their own thing. And over here we have a speaker. We're going to send a single pulse through. Watch what happens. As the air molecules collide, we get this kind of collapsed wave of tightness, and there's this open area here. Watch again. Open area, wave. If we continually send this through, we start noticing patterns. Tight areas with open areas in between them. The particles themselves don't move far. Notice how this red dot never gets much farther from my mouse than anything else, but the pattern, the band of energy, the wave, expands outward from the speaker in these circular bands. Now watch what happens if I increase the frequency. As I increase the frequency, the bands get closer together. There's less space between the bands. Decrease the frequency, and suddenly I have very large bands with very large amounts of space between them. If I change the amplitude, in this case I'm not going to get larger crests and troughs. Instead, the spacing between, the delineation between the compressed areas and the open areas gets much larger. The compressed areas are more compressed. The open areas are more open. What we have here is not a transverse wave. There are no crests and troughs. Instead, what we have is a longitudinal wave. Longitudinal waves are different than transverse waves in that they don't disturb the medium up and down. They disturb it in the direction of travel. So in other words, there's not going to be any bumps up and down. There's just going to be a band stuck together. Instead of crests and troughs, we have compressions, areas of tight packing, and we have rarefactions, areas of loose packing. Amplitude is a measure of how tightly packed the compressions are, how loosely packed the rarefactions are. Frequency is going to be measuring compressions instead of crests or troughs. How many compressions do we see per second? But the idea is still the same. The only real struggle we're going to run into is wavelength, which instead of being from crest to crest or trough to trough, is going to be from middle of compression to middle of compression. You can pick any two compressions or really any two rarefactions if you measure from the middle to measure your wavelength, but the idea hasn't changed. Also, because they're waves, the wave equation still works. V equals F times lambda. Now, this is great if we move through air, but we can't see waves moving through the air. So instead, let's talk about how a slinky would work. In a slinky, instead of shaking it up and down, instead you pull back and let it snap through the slinky, you have a compressed area from where you pull back, a rarefacted area from where it's expanded, and then a compressed area over there. Slinkies work like so. And much like how the medium impacts the wave speed, the tightness of the particles, how close the particles are so they can bump into each other for air and sound waves, or for water or for slinkies, still holds true. Instead of the tying forces together being what causes the wave or the disturbance, instead we have the molecules bumping into each other and colliding. Anyways, thanks for watching. Have a good one.